From the intricate mosaic of archaic human diversity in the Middle Pleistocene, a new and ultimately dominant lineage began to emerge, quietly at first within the African continent. This was the dawn of Homo sapiens, our own species. This period, roughly spanning from 300,000 to 50,000 years ago, marks what many scholars refer to as a great leap forward, a time of unprecedented cognitive and behavioral innovation that would fundamentally reshape the trajectory of human history and lead to our global dominance. The earliest fossil evidence of anatomically modern humans, Homo sapiens, comes from sites in Africa. Discoveries at Jebel Irhoud in Morocco, dated to approximately 315,000 years ago, and Omo Kibish in Ethiopia, around 195,000 years ago, demonstrate that our species originated much earlier and across a wider geographical area in Africa than previously thought. These early Homo sapiens possessed a suite of distinct anatomical features: a more globular brain case, a high and rounded forehead, a smaller, less prognathic face, and the presence of a chin, a uniquely modern human characteristic. While their brains were not necessarily larger than those of Neanderthals, their internal organization and connectivity are believed to have been more complex, facilitating advanced cognitive functions. This anatomical modernity was soon accompanied by a blossoming of behavioral modernity, particularly evident in the African Middle Stone Age, MSA. Unlike the relatively static toolkits of earlier hominins, MSA technology became incredibly diverse and sophisticated. Homo sapiens developed a wide array of specialized tools, including slender blade tools, finely crafted projectile points, which could be hafted onto spears, and tools made from bone, antler, and ivory. The development of composite tools combining different materials, like a stone point attached to a wooden shaft, demonstrates advanced planning and problem-solving skills. The precision and variety of these tools speak to a deeper understanding of material properties and a more nuanced approach to resource exploitation. Beyond stone and bone, early Homo sapiens began to engage in symbolic behavior, a hallmark of modern human cognition. Evidence of this includes the systematic use of pigments, particularly red ochre, not just for practical purposes, but for body adornment and possibly ritualistic activities. Discoveries at Blombos Cave in South Africa, dating back around 100,000 years, reveal engraved ochre pieces with abstract patterns, as well as perforated shell beads, indicating personal ornamentation and the transmission of symbolic meaning. These are the earliest undisputed examples of art and symbolic expression, suggesting a capacity for abstract thought, self-awareness, and the communication of complex ideas. The social structures of early Homo sapiens also became more intricate. They likely lived in larger, more interconnected groups, fostering greater cooperation in hunting and foraging. Their advanced hunting strategies, including the use of projectile weapons, allowed them to target a wider range of prey, including fast-moving animals. The ability to plan ahead, communicate effectively, and share knowledge would have been crucial for their success in diverse and often challenging environments. The development of language, though not directly preserved in the fossil record, is strongly inferred from the complexity of their behaviors and the need for efficient communication within increasingly complex social networks. The critical phase of human expansion began with the out-of-Africa migrations. While there might have been earlier, smaller excursions, The major wave of Homo sapiens dispersal that led to the peopling of the entire globe is generally thought to have begun around 60,000 to 70,000 years ago. This migration was likely driven by a combination of factors: population growth in Africa, environmental shifts that opened up new corridors for movement, such as periods of increased rainfall making the Arabian Peninsula more habitable, and the inherent adaptability and exploratory nature of our species. These early modern human pioneers ventured out of Africa, following coastal routes along the Arabian Peninsula and into Asia. Their journey was not a single, continuous march, but a series of expansions, adaptations, and sometimes dead ends. They encountered new landscapes, new flora and fauna, and, crucially, other hominin populations: the Neanderthals in Europe and Western Asia, and the Denisovans in Eastern Asia. The interactions between Homo sapiens and these archaic human groups are a fascinating and complex aspect of our history. For tens of thousands of years, modern humans coexisted with Neanderthals in Europe and the Middle East, and with Denisovans in Asia. Archaeological evidence suggests some degree of cultural exchange, with modern humans adopting certain tool-making techniques from Neanderthals, and vice versa. However, the most compelling evidence of interaction comes from genetics. Studies of ancient DNA have revealed that Homo sapiens interbred with both Neanderthals and Denisovans. As a result, many non-African modern human populations today carry small but significant percentages of Neanderthal DNA, typically 1 to 4%. And some Asian and Oceanian populations also carry Denisovan DNA. This genetic legacy is a powerful reminder that our family tree is not a simple linear progression, but a complex braided stream of intermingling lineages. The reasons for the eventual disappearance of Neanderthals and Denisovans, leaving Homo sapiens as the sole surviving human species, are still debated. Several hypotheses exist. Climate change. The fluctuating glacial periods may have put immense pressure on Neanderthal populations, who were already living in fragmented groups. Competitive advantage. Homo sapiens' superior cognitive abilities, more flexible tool technologies, broader diet, and more complex social organization may have given them a competitive edge in resource acquisition and survival. Demographic superiority. Even small differences in birth rates or survival rates could have led to Homo sapiens populations slowly outcompeting and absorbing Neanderthals and Denisovans over long periods. Assimilation. Interbreeding may have led to the gradual absorption of Neanderthal and Denisovan genes into the larger Homo sapiens gene pool rather than outright extinction. Regardless of the precise mechanisms, by around 40,000 years ago, Neanderthals had largely vanished from Europe, and the Denisovans from Asia. Homo sapiens was now the dominant, and soon to be the only, human species on Earth. The global dispersal of Homo sapiens continued with remarkable speed. By around 50,000 years ago, modern humans had reached Australia, a journey that required sophisticated seafaring technology, rafts or boats, to cross significant water barriers. This was an astonishing feat of exploration and engineering for the time. Around 15,000 to 20,000 years ago, during the last glacial maximum, humans crossed the Bering Land Bridge, which connected Asia and North America, into the Americas, rapidly populating both continents. By 12,000 years ago, Homo sapiens had spread across nearly every habitable continent, adapting to an incredible array of environments, from the Arctic tundra to tropical rainforests and vast deserts. This global expansion was facilitated by our unique capacity for cultural adaptation. Unlike other species that rely primarily on genetic adaptation to new environments, Homo sapiens could rapidly develop new technologies, social strategies, and knowledge systems to thrive in novel conditions. This cultural flexibility, combined with our advanced communication abilities, allowed for the accumulation and transmission of knowledge across generations, leading to ever-increasing innovation. The Great Leap Forward was not a single event, but a culmination of anatomical, cognitive, and behavioral changes that allowed Homo sapiens to become the most adaptable and widespread species on the planet. This period set the stage for the profound transformations that would follow, leading to the development of agriculture, complex societies, and ultimately, the world we inhabit today. The story of our origins is a testament to resilience, innovation, and the enduring human spirit of exploration. As the narrative of human evolution unfolds, we move into the Middle Pleistocene, a period roughly spanning from 781,000 to 126,000 years ago. This epoch was characterized by dramatic and cyclical swings in global climate, with recurring glacial and interglacial periods. Massive ice sheets advanced and retreated across the northern continents, profoundly altering landscapes, sea levels, and the distribution of flora and fauna. These environmental fluctuations presented immense challenges and powerful selective pressures, driving further diversification and adaptation within the Homo genus. It was during this dynamic era that the descendants of Homo erectus began to evolve into more sophisticated forms, often referred to as archaic humans, setting the stage for the emergence of our own species. The most prominent of these archaic humans is Homo heidelbergensis, a species that lived across Africa, Europe, and potentially Asia from about 700,000 to 200,000 years ago. Homo heidelbergensis represents a critical transitional form, bridging the gap between the more primitive Homo erectus and later, more advanced hominins like Neanderthals and early Homo sapiens. Physically, H. heidelbergensis was robust, with strong brow ridges and a receding forehead, but their brain size showed a significant increase, averaging around 1,200 to 1,300 cubic centimeters, a cranial capacity that overlaps with the lower range of modern human brains. This larger brain size suggests enhanced cognitive abilities crucial for navigating the increasingly complex environments they inhabited. Technologically, Homo heidelbergensis continued to refine the Acheulean tool tradition, inherited from Homo erectus. Their hand axes were often more symmetrical and finely crafted, indicating a greater mastery of stone knapping techniques. Crucially, they also began to develop new methods of tool production, such as the Levallois technique. This innovative method involved preparing a stone core in a specific way to produce large, sharp flakes of predetermined size and shape. The Levallois technique required significant foresight and abstract thinking, as the toolmaker had to visualize the final flake before striking it from the core. This cognitive leap is a hallmark of Middle Paleolithic technology and represents a significant step towards the more complex toolkits of later human species. Beyond tools, there is growing evidence that Homo heidelbergensis engaged in more sophisticated behaviors. They were effective hunters, not just scavengers, Archaeological sites reveal accumulations of large animal bones, such as horses, deer, and even rhinoceroses, with cut marks consistent with butchery, suggesting cooperative hunting strategies. The discovery of wooden spears at Schöningen, Germany, dating back about 400,000 years, provides direct proof of their hunting prowess. These spears, carefully crafted and balanced, demonstrate a remarkable level of planning and technological skill. The control of fire, first mastered by Homo erectus, became more widespread and consistent with Homo heidelbergensis. Evidence of controlled hearths used for warmth, cooking, and protection is more common at their sites. Fire would have been essential for surviving the colder climates of Europe during glacial periods and for making a wider range of foods digestible. The social implications of fire are also profound. It created a central gathering place, fostering social bonding, storytelling, and the transmission of knowledge across generations. Perhaps one of the most intriguing aspects of Homo heidelbergensis is their role as the common ancestor to two distinct and highly successful human lineages that would dominate the Middle to Late Pleistocene: the Neanderthals in Europe and Western Asia, and the Denisovans in Eastern Asia. In Europe, the populations of Homo heidelbergensis gradually evolved into the iconic Neanderthals, Homo neanderthalensis, who thrived from approximately 400,000 to 40,000 years ago. Neanderthals were exceptionally well adapted to the cold, harsh environments of Ice Age Eurasia. Their physical characteristics reflect this adaptation: a stocky, robust build, short limbs, and a wide torso, all features that helped conserve body heat. They had large noses, possibly an adaptation for warming and humidifying cold, dry air. Their skulls were elongated with prominent brow ridges and a distinctive bun at the back, occipital bun, and their brains were, on average, even larger than those of modern humans, ranging from 1,200 to 1,750 cubic centimeters. Neanderthal culture, associated with the Mousterian tool industry, was highly sophisticated. They produced a wide array of specialized stone tools, including scrapers, points, and knives, often using the Levallois technique. They were formidable hunters, capable of taking down large, dangerous prey like mammoths, woolly rhinoceroses, and bison, often employing ambush tactics and close-range thrusting spears. This required significant cooperation, strength, and courage. Beyond subsistence, Neanderthals exhibited behaviors that suggest complex cognitive abilities and a rich inner life. They buried their dead, sometimes with grave goods like animal bones or flowers, hinting at symbolic thought, ritual, and perhaps a belief in an afterlife. Evidence of personal adornment, such as perforated shells and eagle talons, suggests an appreciation for aesthetics and self-expression. They also cared for their sick and injured, as evidenced by healed fractures and individuals who survived severe disabilities, demonstrating compassion and social cohesion within their groups. Recent discoveries even suggest Neanderthals created abstract cave art, further blurring the lines between their cognitive capabilities and those of early modern humans. Concurrently, in the vast expanses of Asia, another branch of archaic humans, the Denisovans, emerged from the Homo heidelbergensis lineage. Discovered relatively recently through genetic analysis of a finger bone and a tooth found in Denisova Cave in Siberia, much about their physical appearance remains unknown. However, their DNA tells a fascinating story. It reveals that Denisovans, interbred with both Neanderthals and early modern humans, indicating a complex and interconnected human landscape across ancient Eurasia. Genetic traces of Denisovan ancestry are still found in modern populations, particularly in Southeast Asia and Oceania, highlighting their widespread presence and the intricate tapestry of human migration and interaction. The Middle Pleistocene was therefore a period of significant human diversity. Multiple lineages of archaic humans, each with their own unique adaptations and cultural practices, coexisted and sometimes interacted across the Old World. They were intelligent, adaptable, and resourceful, mastering fire, developing sophisticated tools, and engaging in complex social behaviors. This era represents a crucial crucible where the cognitive and behavioral foundations for modern humanity were further forged. The stage was now set for the final, most transformative act in our evolutionary story, the emergence and global dispersal of Homo sapiens, a species that would ultimately come to dominate the planet and reshape its future. The interactions and eventual fate of these diverse archaic human groups, particularly the Neanderthals and Denisovans, in the face of the expanding Homo sapiens populations, form the dramatic climax of this chapter. The curtain rises on a new act in the grand drama of human evolution, transitioning from the Pliocene into the early Pleistocene epoch, roughly 2.6 million years ago. This period marks a profound shift, characterized by a cooling and drying global climate that further reshaped African landscapes. The diminishing forests gave way to more widespread savannas, creating new challenges and opportunities for the hominins who inhabited them. It was within this dynamic and increasingly open environment that a lineage distinct from the Australopithecines began to flourish, the genus Homo, our direct ancestors. The defining characteristic of this new genus was not simply bipedalism, which was already well established, but a significant increase in brain size and, crucially, the systematic development and use of stone tools. While the exact origins of the Homo genus remain a subject of active research and debate, the earliest members, often grouped under the umbrella of early Homo, represent a pivotal evolutionary step. Among these, Homo habilis, meaning handy, man, is perhaps the most iconic, though its precise taxonomic placement and role as the first tool maker have been refined by more recent discoveries. Homo habilis lived in East and South Africa from approximately 2.4 to 1.6 million years ago. Compared to the Australopithecines, H. habilis exhibited a noticeable increase in cranial capacity, averaging around 600-700 cubic centimeters, a significant leap from the 400-500 cc of Australopithecus. While still possessing some primitive features like relatively long arms and a somewhat projecting face, their teeth were smaller and narrower, suggesting a dietary shift. Their postcranial skeleton indicates they were still capable climbers. But their hands, particularly the thumb, show adaptations for precision gripping, essential for manipulating objects, and, critically, for making tools. The most compelling evidence for the innovative behavior of Homo habilis comes from the archaeological record of the Oldowan tool industry. These rudimentary yet revolutionary stone tools are named after Olduvai Gorge in Tanzania, where many early examples were discovered. Oldowan tools primarily consisted of choppers, river cobbles from which flakes had been struck off using another stone, a hammerstone, to create a sharp, jagged edge. These flakes themselves were also useful for cutting. While the earliest known stone tools now date back to 3.3 million years ago, predating the Homo genus, Homo habilis is strongly associated with the widespread and consistent manufacture and use of these implements. This suggests a more systematic approach to tool production and a greater reliance on them for survival. The implications of Oldowan tools were profound. They provided early Homo with the ability to process food in ways previously impossible. The sharp edges allowed them to butcher animal carcasses, stripping meat from bones and gaining access to nutrient-rich marrow by smashing bones open. This increased access to protein and fat, which are essential for brain development and maintenance, is considered a critical factor in the subsequent increase in hominin brain size. Tools also aided in digging for roots and tubers, cutting tough plant materials, and perhaps even for defense against predators. The creation of these tools required a degree of foresight, planning, and manual dexterity, indicating a significant cognitive leap. It wasn't just about using a convenient rock. It was about modifying a rock to serve a specific purpose. The environment of early Homo was a dynamic mosaic of grasslands, woodlands, and riparian, riverine areas. This diverse landscape offered varied food resources but also presented challenges, including increased competition and predation. The ability to scavenge meat from predator kills or even to opportunistically hunt smaller animals would have provided a crucial advantage. The tools of Homo habilis were perfectly suited for this opportunistic foraging strategy. As the Pleistocene continued around 1.9 million years ago, an even more advanced hominin emerged, Homo erectus. This species represents a major evolutionary stride, marking a significant departure from earlier forms. Homo erectus was taller and had more modern human-like body proportions, with longer legs and shorter arms relative to their torso. This physique made them highly efficient bipeds, capable of long-distance walking and running, a distinct advantage in open savanna environments. Their brains were considerably larger than Homo habilis, averaging around 900 by 1100 cubic centimeters, and their skulls were lower and more elongated, with prominent brow ridges. But perhaps the most remarkable achievement of Homo erectus was their pioneering spirit. They were the first hominins to migrate out of Africa. This was not a single planned exodus, but rather a gradual expansion over many generations, driven by factors such as population growth, environmental shifts, and the pursuit of new resources. They ventured into new continents, adapting to a wider range of climates and ecosystems than any hominin before them. Fossil evidence of Homo erectus has been found across vast swathes of Eurasia, from Dmanisi in Georgia, dated to around 1.8 million years ago, to sites in Indonesia, like Java Man, 1.6 to 1.8 million years ago, and China, Peking Man, around 700,000 years ago. Their ability to survive and thrive in these new territories speaks volumes about their adaptability and intelligence. They encountered diverse landscapes, new plant and animal life, and different environmental challenges, all of which they successfully navigated. The technological repertoire of Homo erectus also evolved. While they continued to use Oldowan-style tools in some regions, they developed a new, more sophisticated tool industry known as the Acheulean. The hallmark of the Acheulean was the hand axe, a bifacial, worked on both sides, teardrop-shaped tool that was remarkably versatile. Hand axes were meticulously crafted, requiring greater skill, foresight, and cognitive capacity than Oldowan choppers. They served multiple purposes: cutting, chopping, scraping, and digging. The widespread distribution of Acheulean hand axes across Africa, Europe, and Asia is a testament to the cultural transmission of knowledge and the ingenuity of Homo erectus. Another groundbreaking innovation attributed to Homo erectus was the control of fire. While the exact timing and origin of fire control are still debated, evidence from sites like Wonderwork Cave in South Africa suggests controlled use of fire as early as 1 million years ago, with more definitive evidence appearing around 400,000 years ago. The mastery of fire was a transformative development. It provided warmth, allowing Homo erectus to survive in colder climates and expand their geographical range. It offered protection from predators, especially at night. Crucially, fire enabled cooking, which made food more digestible, released more nutrients, and detoxified certain plants, further expanding their diet and contributing to brain development. Cooked food also reduced chewing time and energy expenditure, potentially leading to the reduction in jaw and tooth size observed in later hominins. The social structures of Homo erectus likely became more complex to support their hunting and foraging strategies, as well as their ability to control fire. Cooperation would have been essential for successful hunting of larger game and for maintaining hearths. The increased brain size also suggests a greater capacity for learning, communication, and social bonding. The period of early Homo, particularly Homo habilis and Homo erectus, was a crucible of innovation. From the first deliberate shaping of stone tools to the audacious journeys across continents and the transformative control of fire, these hominins laid the fundamental groundwork for all subsequent human evolution. They demonstrated an unprecedented ability to modify their environment and adapt to new challenges, setting the stage for the emergence of even more cognitively advanced species and the eventual global spread of humanity. The story was far from over. Indeed, it was just gaining momentum. To truly understand the epic saga of human evolution, we must first cast our minds back across an almost unfathomable expanse of time. This isn't merely a story of a few thousand years, or even a few 100,000. It is a narrative stretching back millions upon millions of years, a testament to the slow, relentless, and often unpredictable forces of natural selection acting upon life on Earth. Our journey begins not with the first humans, but with the ancient tree-dwelling primates from whom all apes, including ourselves, ultimately descended. Imagine the world during the Miocene epoch, an era spanning from approximately 23 to 5.3 million years ago. The Earth's climate was undergoing significant shifts. Initially, much of the planet, particularly the equatorial regions, was covered in vast, lush tropical and subtropical forests. Primates flourished in these arboreal environments, their bodies exquisitely adapted for life among the trees, grasping hands and feet, keen vision, and agile movements. However, as the Miocene progressed, global temperatures began a gradual cooling trend, leading to a reduction in rainfall in many areas. This climatic shift had profound consequences, causing the once continuous forests to fragment, giving way to more open woodlands, mosaics of forest and savanna, and eventually expansive grasslands. This environmental transformation would be a powerful crucible for evolution, pushing some primate lineages towards new adaptations. Within this dynamic backdrop, the lineage that would eventually lead to modern humans began its long divergence from the ancestors we share with chimpanzees and bonobos. This split, a pivotal moment in our history, is estimated to have occurred roughly 6 to 8 million years ago. While pinpointing the exact last common ancestor, LCA, remains one of paleoanthropology's most challenging puzzles, fossil discoveries from this period offer tantalizing glimpses into these earliest potential hominins. Consider Sahelanthropus chadensis, discovered in Chad and dated to between 7 and 6 million years ago. Its skull, though heavily distorted, features a relatively small brain case consistent with an ape. However, the position of its foramen magnum, the opening at the base of the skull where the spinal cord connects, suggests that its head was positioned more directly over the body than in typical quadrupeds, hinting at a more upright posture. Then there is Orrorin tuganensis, found in Kenya and dated to around 6 million years ago. Fragments of its femur show internal bone structure consistent with bipedal locomotion, even though its upper limb bones suggest continued arboreal climbing. Finally, Ardipithecus, represented by species like Ardipithecus cadaba, 5.8 to 5.2 million years ago, and Ardipithecus ramidus, 4.4 million years ago, provides a more complete picture. Erdus ramidus, in particular, offers a mosaic of features. A grasping big toe suitable for climbing, but a pelvis and hip joint that indicate an ability to walk upright on the ground. These early hominins were likely still very much at home in the trees, but were experimenting with a new way of moving on the ground: bipedalism. The Pliocene epoch from 5.3 to 2.6 million years ago witnessed the flourishing of a diverse group of hominins known collectively as the Australopithecus. This genus truly solidified the commitment to bipedalism, making it a defining characteristic. The environmental pressures of the Pliocene, with its continued expansion of open grasslands and more seasonal rainfall, likely favored creatures who could efficiently move between scattered food resources, see over tall grasses to spot predators or prey, and free their hands for carrying food, tools, or offspring. One of the earliest and most well-understood species is Australopithecus anamensis, living between 4.2 and 3.9 million years ago. Fossils from Kenya and Ethiopia show a mix of primitive and advanced traits. Its tibia, shin bone, indicates bipedalism, while its long forearm bones suggest an adaptation for climbing. This species likely inhabited a mosaic environment of woodlands and open grasslands, reflecting the transitional nature of their locomotion. However, it is Australopithecus afarensis, living from approximately 3.9 to 2.9 million years ago, that truly captured the world's imagination with the discovery of Lucy in 1974. This remarkably complete skeleton, along with numerous other A. afarensis fossils, provided irrefutable evidence of habitual bipedalism. Lucy's pelvis is broad and bowl-shaped, designed to support internal organs during upright walking, unlike the long, narrow pelvis of a chimpanzee. Her femurs, thigh bones, angle inward from the hip to the knee, placing the feet directly beneath the body's center of gravity, a critical adaptation for efficient bipedal stride. Furthermore, her feet, though retaining a slightly divergent big toe in some interpretations, were clearly structured for weight-bearing and propulsion during walking. Yet A. afarensis was not simply a smaller, hairier version of modern humans. They retained significant arboreal adaptations. Their arms were relatively long compared to their legs, and their finger and toe bones were curved, suggesting they still spent a considerable amount of time in trees, perhaps for foraging, sleeping, or escaping predators. Their brains were small, averaging around 400–500 cubic centimeters, comparable to a modern chimpanzee's. Their faces were prognathic, with prominent brow ridges and large chewing muscles. The teeth, however, showed a shift: smaller canines and larger molars with thicker enamel, indicating a diet that included tougher, more abrasive foods found in open environments such as nuts, seeds, and roots, alongside fruits and leaves. Perhaps the most dramatic evidence of A. afarensis' bipedalism comes not from bones, but from footprints. At Letoli, Tanzania, a remarkable trail of fossilized footprints preserved in volcanic ash dating back 3.6 million years provides a direct snapshot of these hominins walking upright. The footprints show a clear heel strike, arch, and toe-off, remarkably similar to modern human gait, confirming that bipedalism was well established long before significant brain expansion. While Australopithecus afarensis was thriving, other Australopithecine species also emerged. Australopithecus africanus, found in South Africa and dating from about 3.3 to 2.1 million years ago, shared many similarities with A. afarensis, but had a slightly more rounded skull and less prognathic face. Later, around 2.5 million years ago, a new branch of hominins, often classified under the genus Paranthropus, sometimes called robust Australopithecines, appeared. These species, including Paranthropus ethiopicus, P. boisei, and P. robustus, represent a fascinating evolutionary experiment in specialized feeding. Paranthropus species were characterized by massive jaws, enormous molars with thick enamel, and powerful chewing muscles that attached to prominent bony crests on the top of their skulls, sagittal crests, giving them a distinctive, almost gorilla-like facial appearance. These adaptations suggest a diet heavily reliant on tough, fibrous plant foods, such as grasses, sedges, and hard nuts, which required extensive grinding and crushing. They lived alongside early members of our own genus, Homo, for over 1 million years, occupying a different ecological niche. Their evolutionary path ultimately led to a dead end, as they eventually died out, unable to adapt to further environmental changes or perhaps outcompeted by the more versatile early Homo. The period from 6 to 2 million years ago was a time of immense diversification within the hominin lineage. It was not a linear progression from ape to human, but rather a complex bush of species, each experimenting with different adaptations to a changing African landscape. Bipedalism emerged as a key innovation, setting the stage for subsequent developments. While brain size remained relatively small, the foundation for future cognitive leaps was being laid. The stage was now set for the emergence of a new kind of hominin, one that would begin to interact with its environment in fundamentally new ways, leading us closer to the dawn of the handyman. With Homo sapiens now inhabiting nearly every corner of the globe, the stage was set for the most dramatic transformation in human history, the shift from a nomadic hunter-gatherer existence to settled agricultural societies. This period, beginning around 12,000 years ago at the end of the last ice age, marks the Neolithic Revolution, a profound turning point that would fundamentally reshape human societies, our relationship with the environment, and the very trajectory of our species. As the climate stabilized and became warmer and wetter, certain regions, particularly the Fertile Crescent in the Middle East, saw the proliferation of wild grasses like wheat and barley. Simultaneously, animals such as wild sheep, goats, pigs, and cattle were abundant. Through a process of trial and error, observation, and increasing understanding of their environment, human communities began to experiment with cultivating these plants and domesticating these animals. This was not an overnight change, but a gradual process that unfolded over millennia. The development of agriculture had monumental consequences. It allowed for a more reliable and abundant food supply, leading to significant population growth. With a surplus of food, people no longer needed to constantly move in search of sustenance. This led to the establishment of permanent settlements, which gradually grew into villages, then towns, and eventually the first cities. Sedentary life brought about new social structures, with specialized labor emerging as not everyone was needed for food production. Artisans, builders, and leaders began to play distinct roles. The need to manage crops, store surpluses, and organize larger populations spurred further innovation. Writing systems developed to keep records, complex legal codes emerged to govern, interactions and monumental architecture began to appear, reflecting growing social complexity and collective effort. This era saw the rise of the first civilizations: Mesopotamia, ancient Egypt, the Indus Valley, and early Chinese dynasties, each developing unique cultural, technological, and political systems. The cognitive abilities that had been honed over millions of years of evolution, problem-solving, planning, communication, and symbolic thought, were now applied on an unprecedented scale. Innovations like irrigation systems, the wheel, metallurgy, working with metals, and sophisticated mathematics transformed human capabilities. Knowledge accumulated and was passed down through generations, leading to accelerating technological and social progress. However, this new way of life also brought challenges. Increased population density led to new diseases, and reliance on a few staple crops made societies vulnerable to famine if harvests failed. The domestication of animals brought new zoonotic diseases. Furthermore, the expansion of agriculture often came at the expense of natural habitats, leading to deforestation and environmental degradation, a pattern that would continue and intensify throughout human history. The story culminates in the present day, an era often referred to as the Anthropocene, a proposed new geological epoch defined by the significant human impact on Earth's geology and ecosystems. From the agricultural revolution to the industrial revolution and the digital age, Homo sapiens has become an unparalleled force of planetary change. We have reshaped landscapes, altered climates, and influenced the very biodiversity of the planet. Our journey from a small band of bipedal primates in Africa to a global species capable of space travel and genetic engineering is a testament to our remarkable adaptability, intelligence, and capacity for innovation. Yet with this power comes immense responsibility. The challenges of the 21st century, climate change, resource depletion, and maintaining global stability, are direct consequences of our species' success and its profound impact. The story of human evolution is not just a tale of the past. It is a continuous narrative that we are still writing. Understanding our deep history, the forces that shaped us, and the choices our ancestors made, provides invaluable context as we navigate the complexities of our present and shape the future of Homo sapiens on this planet. The journey continues.